Hi guys, welcome to your Lab 8. Going over Chapter 11 today. I know I saw you guys last week's lab video. I'm going to try and get that done today or tomorrow. But for now, let's talk about muscles. That'll be great. Okay. I don't know if it's better if you can see me or not. Okay. This is no longer exercise 12 or exercise 13. We are in Chapter 11. Okay, so the first thing we're going to talk about is histology. So if you guys going back to the last unit, remember there are three types of muscle. One of those being skeletal, which you'll see up in this top corner up here. Maybe? Yeah, okay. We also have smooth and cardiac. Now, let me remind you some things about these. Skeletal is completely voluntary. You can also see that it's got these really long fibers. We're going to talk more about those today, and the anatomy of the muscle, skeletal muscle itself. Smooth, if you guys remember, this is like a propulsion type thing. Not always, but it's a pretty good rule of thumb. You can see it's not as well organized as our skeletal muscle. You still have striations. You mainly find this in blood vessels is a huge place, and the other place is in your intestines. Some other places, sphincters, so any sphincter you don't control is going to be smooth muscle. The ones that you do control, obviously, are going to be skeletal. The last one that we're going to talk about right here is cardiac. This cardiac muscle, these guys can be binucleated. They tend to be mononucleated, meaning it only has one nucleus rather than two. One thing I forgot to mention about the skeletal is multinucleated. These fibers run as long as like the muscle do. They're highly nucleated. Another thing that these cardiac muscle histology slides will have that none of these other two have are these intercalated discs, and you can kind of see them here. Let's see, go here and here. You can kind of see that they happen in between the muscle cells. That's very specific to cardiac muscle. It kind of allows, so think of like getting a Charlie horse in your heart. Like that would be really bad, right? So that's all those fibers contracting together. Number of reasons why I can do this, but if that happened to your heart, that'd be really bad, as you can imagine. So in cardiac, these intercalated discs actually kind of help mitigate those types of issues that you would have, kind of allowing each cell to work independently of one another. It's pretty freaking cool. Okay, so I think we're gonna go over our skeletal muscle overview. So once again, this is anything that is voluntary. We're going to see this, once again, multinucleated. This is a connective tissue. No, wrong. This is a muscular tissue. Connective tissues are things like our bones, our tendons, and stuff like that, but they are associated. So remember that. Obviously, movement for muscles, huge, right? Protection and support. This also helps with... So obviously helping our bones, but also heat production. So we kind of talked about how epithelial and the skin helps with this. Muscles can do this as well. Remember shivering? That's your muscles doing minor contractions that are actually rubbing back and forth, creating friction and producing heat as a form of energy. Okay. So we're going to kind of talk about how these things are structured. You're going to see this arrangement quite a bit. So this is for muscles, but we're going to see this when we talk about nerve fibers next unit. So what you'll get is these kind of units within units within units, okay? So right now we're going to talk about one muscle cell, and that is one muscle fiber. So that's that whole fiber, because we're talking skeletal right now. So you can see right here that this whole bundle right here is a muscle fiber. You can see that there's a little bit of rods in between those. We're going to talk about what those are, but those are not cells themselves. They're part of the cell. Ooh, oh, so I'm going to talk about the other parts. We'll talk about that soon, I hope. Okay, so we're going to go in there and we're going to talk about what those little rod-like structures are that I was talking that aren't cells. These are known as myofibrils, okay? They're a specific organelle to muscle fibers. So myo meaning muscle and fibril meaning fiber, muscle fiber. Okay. The other thing that is kind of special to the muscle cell is the sarcolemma. So you can see it's this kind of thin wrap that's bundling all of our muscle cells, or myofibrils together, right? So the sarcolemma is bundling all those together. You can see all the purple in here. Those are all nucleuses. Reminder, once again, skeletal muscle is multinucleated. And then you can see we have these little orange guys happening in between our myofibrils, and those are our mitochondria. We're going to actually be using a lot of those. And then one other thing that this guy hasn't quite shown us, but we're going to talk about is, oh God, what's it called? Well, it's going to be T-tubules and stuff like that, but we're not there yet. So let's not. Okay. Within these myofibrils, right? So we have our muscle cell, and then in our muscle cell or our muscle fiber, we have myofibrils. So we're now looking at one myofibril. Within these myofibrils, we have what are known as myofilaments. So these are really thin, small thread-like structures throughout the myofibrils. There's two of these, and they actually work together to make a muscle contract. You guys have probably heard these before. If you haven't, that's right. So one being actin, and in this picture here, the actin is being represented by the blue threads. As you can see, they interplay between those red, which are the myosin. The myosin are these nice thick filaments. But notice how the actin has this zigzag guy happening here. We're going to talk more about that structure and what these are doing. But basically what happens is the actin and the myosin, through ATP and action potentials, they slide on each other to make the filament, the fibrils, actually smaller. Shorter. Not smaller, shorter. Okay. Okay, so these are the things you guys need to start needing to know about these. So when we always talk about muscle cell, we always talk about the muscle cell being striated. These striations are caused by these dark and light bands. A dark band is known as an A band. This is where you get these myosin, right? So the myosin is the red, overlapping with actin filaments. This will create darker. The I band, or the light band, is only the actin. You can only see the actin in that, okay? So here we are, we've broken down even further. So when you go from I band to I band, this is known as a sarcomere. This is a contractual unit of muscle. So when we're talking about this, this is one unit of contraction. Okay, contract, uncontract, contract. Okay. So we have two I bands. As you can see up here in this picture, these I bands are actually split in half to fill one sarcomere. So it's not a full I band that makes a sarcomere, it's only half an I band to make up one full I band. Okay, hopefully that makes sense. So if you look in at that sarcomere, you look in at, you can see we have where it's just the myosin, you don't have any actin happening, is known as the H zone, which going through that is the M line. Then if you go on either side of the myosins, you can see what's called the Z disc. And so that's that zigzag. You see it part of the I band. And that's where the myosin is actually kind of connecting to at the tip points of those. Okay, I think that's good for it. So here's some more. Okay, so this is actually a picture of what contraction looks like. So the top being uncontracted and the bottom being contracted, you can see how those things are sliding over each other to make the myosin more fully fill in those actin lines. You can see that the H zone almost completely disappears in contraction as well. Okay. Sweet. Okay, so, oh yeah, so sarcoplasmic reticulum that I was thinking of. It's a special type of smooth ER. So we're going to talk about that. We're going to talk about these transverse tubules. They're also known as T-tubules. And then these terminal cisternae. So these transverse tubules, also known as T-tubules, what does transverse mean? It's going like side to side, right? These are formed where the sarcolemma indents into the muscle cell. I'm going to show you a picture where that's going to make a little bit more sense. Once again, we've got the sarcoplasmic reticulum, which is just the specialized smooth endoplasmic reticulum. We're going to talk about that guy. And this terminal cisternae are just cross channels of this specialized ER. Okay, this is what it looks like. So you can see here we're kind of looking at one sarcomere, right? So that's one contractional unit. With each one of these rounds being a myofibril, right? With the red being myosin and the little blue guys being actin filaments. You can also see some mitochondria happening in here. I am not seeing any nucleus on this picture, but that's all right. So you can kind of see all this blue webbing. All that blue webbing is specialized, that specialized ER. So if you guys remember what the smooth ER's job is, at all? Probably not a whole lot. A big part of it has to do with calcium, and that is basically this guy's job. He's going to be doing calcium storage. Is mainly his job is holding that calcium. You can see where the SR dips in between the myofibrils. You can see where you get those terminal cisternaes of the sarcoplasmic reticulum, right? You can see those? Perfect. The T-tubules almost kind of work as like a bundling guy, but it actually allows for things like calcium to more quickly touch all the myofibrils than it needs to. I think we're going to talk about this a little bit more when we hit into physiology a little bit in a minute. Okay, so remember how I was showing you we're going to see those units inside units inside units? We're going to talk about that right now. Okay, so skeletal muscles are actually made up of thousands of these muscle fibrils, these myofibrils, that are bound by connective tissues. So connective tissues being things like, right, dense irregular, tendons, that kind of stuff, right? Okay. Well, there's these special coverings for each stage of this. So the first one we're talking about is endomyosin. So endomyosin, so if you guys remember, we had a whole bunch of those muscle fibers. When you bundle those together, you get your endomyosin, which is made up of this areolar connective tissue. Hopefully you guys can kind of remember what that looks like histologically. Then your next step up is we get these fascicles is what they're called. Fascicle is not special to muscles. You'll see the word fascicle again, but just think of it as like a bundling of a bundling. So this bundling that bundles these fascicles together is known as the paramecium. Peri is usually like a mid prefix. And this one's made up of collagen. I hope you guys can kind of remember what collagen is. Collagen is like the stuff that kind of gives us a little bit of bounce to our skin. The last one is the epimecium. I think I'm going to show you a picture in a minute where I'm going to be able to go through these things again. This one's dense irregular. This one's bundling a bunch of those fascicles. So you're going to have a whole bunch of these myofibrils that are bound together. And then next we're going to have these fascicles that are built. And those are going to be bundled together by the paramecium. And then lastly, enveloping all the fascicles to make up the whole muscle will be the epimecium. Here's that picture. I'm going to hide my head for a minute. So you can see here, we have our muscle fiber running in our whole muscle cell. So our whole muscle cell is being held by the sarcolemma slash endomyosins that are happening in between those individual muscle fibers. Then when you get a whole bunch of those muscle fibers together, again, those are going to create a fascicle, and that fascicle is going to be covered by a paramecium. And then when you get a whole bunch of those fascicles together, you're going to bundle those up with the epimyocin. Epimecium. There we go. You guys should be able to identify what a fascicle looks like under the microscope. That should be easy peasy, no problem. Okay. The epimecium blends together with the ends of muscles. It will give you two types of formations typically. One being tendons, which are really strong. These ones are going to be attaching muscle to bone. The other one that you'll see is these aponeuroses. So one of the places that you guys will see this, so this muscle on top of this guy's head, on top of all of our heads to be real, is the occipitofrontalis, something like that, which is actually made up of two muscle bellies, one being the frontal belly, which is obviously the one that's touching the frontal bone, and then the occipital belly, which is obviously touching the occipital back here. These are actually considered kind of the part of the same muscle because they are connected via this aponeuroses, which is a sheet-like connective tissue. Another place that you'll get this is actually in your abdomen. Is another place that you can get these aponeuroses. Okay. Yeah, so we talked about that. Aponeuroses, this is muscle to muscle. They have to span rough bony projections. Yeah. More tendons and muscles can pass over joints. So you'll see a lot more tendons happening in the joint area. Almost all your hands, all the stuff in here is all tendons. It's not very muscly, as you can imagine. You can imagine how how thick your hand would look if it was instead of tendons it had muscles. That wouldn't be great. Anyway. And this is another place just for nerves and blood vessels to pass through. Okay, we're going to quickly talk about this. So you guys should be working on all your muscle cards. Some you will see have either an origin or an insertion available to fill out. You guys should know what an origin and an insertion is. And you should know the bony landmarks that are that attach to these. So a lot of bony landmarks actually act as an origin or an insertion. When you're describing muscle actions and stuff like this, knowing origin can help, and so can insertion, because it'll actually tell you kind of how the bone can move, or sorry, the muscle can move / bone. So when you're talking about the origin is the place where you don't have any movement. So you can see on here, they're showing you the brachialis. The origin of it is actually, I bet this is the linea aspera on your humerus. This part will not move. It's the insertion that will be moving. So the insertion is what's actually contracting or getting smaller to move the appendage. So the appendage is the thing that's moving, right? It's not the actual arm itself. If the origin is moving, then it's not the origin. Sorry, I can't make more sense. Okay, so we're going to talk about these special units. You guys need to make sure that you have Phil's up and running, because I'm telling you, Phil's is going to be able to help you explain these things to you in a way that I just won't be able to, and / don't have time to be honest. Okay, so we have these neuromuscular junctions. This is basically where a motor neuron, so motor, movement, neuron meets a muscle fiber. You can have one motor neuron that actually stimulates multiple muscle fibers. This is known as a motor unit. So rarely will you get like a motor unit that is serving like the bicep and the gracilis down in your leg. No. So a motor unit is usually specific to a muscle. The other thing that you have, and you can kind of see it here in this histology, so in this neuromuscular junction on this slide here, you can see the red going sideways is the muscle fiber, and then these dark spots, that's the actual junction. This is where the synaptic cleft forms. And then the tendrils coming off those are the synapses of the, sorry, not synapses, axons of the neuron. Okay, so the synaptic cleft is actually, these things aren't super connected. It's a space. I'm gonna show you a picture where this is gonna make a little more sense, where it's fluid filled, and it's the neuron and the muscle fiber are actually somewhat separate. This is where the motor neuron, which is passing a action potential from your brain, saying move this thing, it passes this action potential from the neuron to the muscle fiber. This is where it happens. As we know, action potentials are electrical, so we actually take advantage of some of our neurotransmitters in order to basically pass this electrical pattern over. So this is what this picture looks like. So you can see the yellow here is the axon terminal of the neuron, motor neuron. If it is a sensory neuron, it's not moving anything. You guys need to remember this for next unit. So you'll see you got these like bubble-like things happening at the bottom here. These are vesicles. Vesicle, once again, not a super, it's actually a pretty broad term, just to mean like a sac is something. With acetylcholine, ACH. You guys should absolutely know what acetylcholine is. From like this point on, anytime I say acetylcholine, I want you guys to know what that means. Acetylcholine is a neurotransmitter. It's one of the most abundantly used ones in your system. This guy is really high acting. So you'll get these vesicles with acetylcholine in them. You'll actually get a buildup of them. You can kind of see that in the background here. And as they build up, they're actually pushing down. And so the vesicles actually meet with the terminal end and they pop out. So you can see the acetylcholine comes out into the synaptic cleft, which is, remember, that fluid filled, which has these acetylcholine receptors. Okay. These acetylcholine receptors pick up the acetylcholine from this and then basically it generates an action potential that gets sent down from wherever the junction is down to the end of the fibril. So just to remind you, these receptors are happening in the sarcoplasma of the muscle fiber. Okay. So we're going to talk about this a little bit more, I think. So, reminding you, so this used to be 2 different labs. So, this is a review of kind of what we just went over, which is voluntary skeletal muscles. They are stimulated by motor neurons. These motor neurons break up into many axon terminals, of which each forms this neuromuscular junction. The neuromuscular junction is just that kind of fluid-filled space happening between the muscle fiber and the nerve fiber. And then the motor unit itself is that one neuron with as many axons, as many neuromuscular junctions as it's attached to. So this is what it looks like when it's up close. So each one of those would form one of those neuromuscular junctions that we just looked at. Yeah, that looks great. Okay. So now we're going to actually talk about what starts happening when we contract our muscle. So 3 main things happen. 3 main things happen. The muscle cell becomes electrically excited. This is via the acetylcholine receptors attaching to their receptors. which generates this action potential. Then you get this excitation contraction coupling, which is a connection between the action potential and the mechanical muscle contraction. So the mechanical muscle contraction, if you can remember, is the actin and the myosin are going to start wanting to go over each other, which is C. Okay, which is the myofilaments, actin and myosin slide against each other, and this results in that muscle contraction, right? So we're going to get shorter. So we're passing on the action potential from brain down into my thumb, which is giving me a thumbs up. That action potential will then be shifted from the neuron into the muscle fibril via acetylcholine receptors. This electrical action potential then travels down the myofibril, interacting with the sarcoplasmic reticulums, basically of the myofibrils, which then cause these myofilaments to slide on each other, causing contraction. So much. Okay. So this is all the things I just said. I'm not going to go over all this, but you guys should read the shit out of this. I might give myself a few seconds just because I want to, yeah. Oh yeah, that's a good one. This one even tells you how the T-tubules are working and how the calcium is being activated by that action potential. Super cool. You guys should absolutely know how your muscles work. This is awesome stuff. Okay. Okay, let's talk about resting potential. So we kind of talked about what an action potential, about action potentials. I don't know if you guys actually know what an action potential is. I think we're going to be hitting a slide here in a minute that will, though. So first thing I want to talk about is resting potential. So this is just your resting membrane potential. This is your cell, right? So your cells just sitting there, chilling, waiting for its action potential to get its steady state. This is your resting potential is typically, not typically, it's negative millivolts always. Okay. You can see that, I think, on this picture. It's mainly because the plasma membrane is more permeable to potassium than to sodium. So the inside of the cell tends to be more negative than the outside of the cell because there's more potassium inside the cell and there's more sodium on the outside. It just creates a slightly negative charge. Yay, we're going to talk about this action potential. I'm going to hide my head real quick so you can get a better view of this. So you can see here the action potential. I want you guys to know these bolded words really well. Rapid depolarization and repolarization of the membrane. Okay, so you can see in this little graph over here, this is the depolarization happening up and the repolarization is happening on the way down. Okay. You can also see there's a few other things that I would like you guys to know. So you can see the resting potential here. You can see that it's happening at slightly negative, right? The other thing that I'm going to point out real quick is this threshold. This threshold, this is basically the amount of stimulus that is needed to initiate this depolarization peak, okay? And that happens to be important when you guys are going to do your fills later. Let's talk about refractory period as well real quick. So you can see during this hump, it's known as what's known as the absolute refractory period. An absolute refractory period. So you cannot have another action potential happening during this time. It's physically impossible to initiate one of these. Okay? Not physically impossible. We're going to talk about some exceptions to that rule. Then you can see this relative refractory period. This is the refractory period in which You can get another action potential, but it's going to be much harder. So typically you need some kind of return to baseline before you can hit another action potential. We're going to talk about that in a little bit, I think. Okay, so during depolarization, this is the stimulus. The stimulation of the muscle cell causes the sarcolemma to be more permeable to sodium. So during depolarization, we're going to let the sarcolemma allow more sodium into the cell, making it more positively charged. Right? So we're going from negative to positive. You can see this threshold. You actually don't need a whole lot, but you do need quite a bump to make it happen. Okay. During repolarization, the sarcolemma is like, no more sodium. And it's like, now bring on that potassium. So the potassium is now leaking out of the cell, causing it to become less positively charged. So we hit this peak of like a bunch of charge, and now it's like no more sodium. So we're gonna let some K come out, and then we're returning back to our normal baseline of resting potential of having, what is it? More potassium on the outside than sodium on the inside, I think. That's what I was saying. I can't remember right at this moment. Picture to provide. So during this time, so you can see we have the sarcolemma happening down the middle. The grayish area is outside the cell. The yellow is inside the cell. During resting potential, we have high amounts of sodium, high amounts of potassium inside the cell, sodium on the outside of the cell, making the inside of the cell just slightly more negative, right? So it's it itself is negative. During our action potential, we're becoming more permeable to sodium. I'm going to let the sodium in. We're going to have a peak positive peak. Oh God, why is my brain not working? Peak positive membrane potential, right? And then during repolarization, so we're coming back down. We're saying no more sodium. We're going to let some of that calcium or potassium leak through, and now we're back to kind of resting baseline. Okay. Oh yeah, absolutely cannot be initiated. So you cannot get a second action potential during this refractory period. Absolutely not. No matter how large the stimulus is, it's just saying, nope, busy now, got other stuff that I'm doing. Not so much the case in the relative refractory. You can get it, it's just harder. It's much harder, and you need I would say your threshold stimulus has to be substantially higher than the initial threshold. Okay, so we're gonna get into some muscle terminology that I want you guys to know for sure. So this is a different graph than what we were just kind of looking at. Remember, we were looking at that graph that had like millivolts on the side. It was the action potential one, right? So the action potential, it was over time, but the y-axis was not tension, it was millivolts. We're now moving into this graph where tension is the y-axis. And so tension is usually, think of it as like force, if any of you have had physics. You can even think of this as like a weight, right? So weight causes tension in the muscle. Okay, so on this graph, we have one twitch displaying, okay, which is made up of 3 periods. A latent period shown in yellow, you can see it's kind of small. This is before contraction. The contraction takes place, but it's prior, it's right, this is the time between stimulus being applied and contraction of the muscle happening. So you can imagine, especially with things like reflexes, this latent period's like over like that, no problem. Okay. This is allowing for that sodium-potassium exchange to be happening. The next phase of this is contraction. So this is where the muscle is actually shortening. So you're getting actin and myosin sliding over each other. And the last one is relaxation, which is your muscle tension returning back to that resting potential, and your sarcomeres are coming uncoupled from each other and coming back. Okay. Stimulus. So we've talked about stimulus. Now I want to make one mention about stimulus before we talk a little bit further. Stimulus can literally come from like anywhere. Like anything that's gonna stimulate your muscles. So I don't know if Phil's has done this, but some of the ones that you can think of are electrical. Obviously, electrical. If you like tase somebody, their muscles are gonna involuntarily contract. Heat. You can also do this through heat and through cold. Chemically, you can also do this. Chemically, there's a few ways. You actually have chemicals that mimic acetylcholine, and so will bind to those receptors. Trying to think if there's more. Oh yeah, and then there's just like mechanical. Like if you poke the muscle in a right way, it will contract, right? Okay. Or too hard, right? I also want you guys to think, when you're thinking of a muscle, think of it very much like a rubber band too. Like even if like you're thinking like I have a tendon here and a tendon here, it's gonna pull like this, right? So when it's pulling like this, like this, right? When it's pulling out, it's not contracting. It's only when it's getting shorter that it's contracting. Okay. Okay, let's talk about stimulus. So once again, stimulus can come from electrical, chemical, punching the muscle, who knows? If you don't punch the muscle hard enough, it will be too weak to elicit a response. Okay, don't practice this at home. That would be a subthreshold stimulus. So the threshold stimulus is the voltage at which the first perceptile contractual response is obtained. Okay, so subthreshold is none of those motor neurons or units are going, hey, you need to start working, start sliding that stuff. None of that's happening. You can see at threshold, you've recruited one. So the larger the stimulus, the more motor units you can recruit to help you out. Now, you do have a limit, obviously, to the amount of motor units you have. So keep that in mind. There hits a plateau, right? Okay. Oh, that's what we're going to talk about next. So we're going to talk about treppe. Treppe is basically the French word for stairs. Don't those look like stairs? Okay. Treppe is important because it returns, you get complete relaxation after basically a contraction. So this is a gradual step-like increase in the strength of contraction. So you can imagine, so each one of these pink arrows is a stimulus. Let's imagine, let's be less violent. Let's not punch people. Let's tase them. We're gonna tase people instead. So each time we have a pink arrow on this graph, we're gonna tase somebody. And you can see after each one of those, we're actually recruiting more and more motor units. Think of it as like in that first step, after that first one's like, somebody's kind of waking up. They're like, oh yeah, I should go to work. Go work. So in the second one, they're more like, oh yeah, we have our first cup of coffee. A few other guys are now waking up. Okay, that's kind of what's happening here. Is each time you repeat the stimulus, you're recruiting more of those motor units. Once again, for treppe to be considered treppe, you need complete relaxation happening between each of the contractions. And then we're going to increase in strength until eventually we've recruited all the motor units that we have. They're all awake. They've all had their coffee. They're now ready to work for you. Yeah. Okay. So you can see why this happens is because it's actually the availability of calcium in your sarcoplasma, right? So I said that's the whole point of that ER is to provide calcium. Sorry, I'm reading this and it's not making sense to me. It says the calcium was not completely put back into the right, so we have an increasing availability of the calcium. The muscle enzyme systems become more efficient, so you're getting heat as the muscle contracts. And I think this is also where you get lactic acid eventually. Yeah, I'm not understanding that. I'm gonna have to come back to that. I want to address that in class. Okay, so now we're gonna talk about, we've talked about trepe. We know what the character is. So we know what a muscle twitch is. We know what trepe is. Now we're gonna talk about graded muscle response. These are just variations in degree of muscle contraction. So you have the ability to do this, right? So could you imagine? Okay, this has a special weight. This is one of the agates Colin has found. Could you imagine every time you went to go pick this up, you picked it up with the full force of all your motor units? You're like, yeah! Right? No. It's nice to be able to decide how many motor units you're going to pick up, right? This is that graded muscle response. So changing the strength of the stimulus, so obviously changing weight of things can recruit different muscle or motor units. And then the other thing is changing the frequency of stimulation. So remember how we were talking about those refractory periods, and we have that kind of refractory period. We're going to start pushing the limits of that and seeing what happens when we increase the stimulus frequency. How are there still flies? Okay. Okay, so we already kind of talked about this. Strength of stimulus intensity. So we've changed the weight, or maybe we've upped the amplitude of our voltage of our taser. Instead of throwing a tennis ball at somebody, we're gonna throw a bowling ball. I don't know. Remember, you do have a limited amount of motor units, so you will get what's called maximal stimulus. So this is the amount of weight or voltage or stimulus, let's say stimulus, that causes all of your motor units to be recruited, okay? And it's gonna provide your maximal contraction. Oh, look, we were talking about these things. So, size principle, right? As the stimulus strength, the amount of strength needed for the stimulus is increased, the more motor units are recruited. So imagine picking up a hacky sack. Ooh, let's kick the hacky sack, right? Super easy, probably doesn't need a whole lot of motor units. Now we're gonna kick that bowling ball. Definitely to recruit a lot of motor units to do that, but not impossible. Now this big boulder, right? Yeah, probably going to be maximal contraction, and I doubt you're still going to get that thing to move. Okay, so that's the basis behind some of that gradual muscle. We're going to talk a little bit more about recruitment here. You can see in this picture, we're still using this tension by time. Actually, this is not by time. This is tension by proportion of nerve fibers excited. So think of this in terms of motor unit recruitment. So at maximal contraction, you can see all cylinders are firing. This is it. That's the amount of motor units you have. You're not going to be able to increase tension any more than that. That has been it. Okay. Hopefully you guys understand that. Okay. So we hit all that. We talked about all that. So once you hit that plateau, the first one, a plateau, that's your maximal stimulus that you've hit. Okay. Now let's talk about changing the frequency of the stimulus. So this is that thing where I was talking about we're going to play around with the refractory period. We're going to talk about two things that can happen when we do this. One is wave summation. So this is the increase of muscle contraction strength based on how rapidly the muscle is stimulated. So we're going to pound it with stimulus, see what happens. And then we're going to talk about what tetanus is, which is this extreme form of wave summation. So we're going to play around with what wave summation is, and then we're going to see this extreme form of tetanus. So here, once again, we have this tension on our y, stimulus on our x, / time, right? So we're moving in time this way. Nope, this way. I don't know. So this is before. So wave summation happens. It's not like trepe. So trepe, remember, trepe is when we're coming all the way back down. We get to hit our relaxation state again. Wave summation is like, no, we're not doing that. We're just, as soon as we hit that depolarization, we're gonna, or that repolarization peak, we're gonna start depolarizing again. And you can see that that's what's happening over here on the right of the graph. You'll see that the response to the second stimuli will be greater than the first. So here we have a twitch, wave summation. Notice that the valleys are not going all the way down to the bottom as you would see in TREPE. In incomplete tetanus, and I want to remind you again, these orange arrows down here is how often the stimulus is being repeated. So whether this be like punch, 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 or tase, 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 or what was the other ones I said? Chemically, shot, shot, shot. I don't know. So these are higher frequencies. So you're not giving the cell membrane time to repolarize, right? Before it's depolarizing again. And you can see in this wave summation, you may get one or two of these, you get easily distinguished like peaks and valleys, which each one kind of being more intense than the next. And then in this incomplete tetanus, it's happening much quicker. And in complete tetanus, this is very characteristic of complete tetanus, is there are no peaks or valleys. You can't see any peaks or valleys. These are in a constant state of stimulus. And if you want to think about how that would feel, so tetanus, this is like you get lockjaw, right? So this is where your muscles are just in complete contraction. Charlie horse, man. Oh, it hurts so bad, right? That's because your body's not supposed to work like that. Okay. So we just talked about pushing your muscles to the max in terms of action potentials, stuff like that. We're going to talk about isotonic contraction. So iso meaning the same, and tonic meaning tension or force. So you can see here on our, actually I'm going to move my head real quick. We have time on our x-axis again with tension on the y. The amount of force that is required to move the load is our dotted line here. So this is basically, so think about standing, right? Do you feel like you're like working out when you're just standing there? No. Well, believe it or not, anytime you're like in a posture or something like that, or like that, you are isotonically contracting muscles, which is just, think of this as like a passive load bearing. So you get tension that develops to the point where it remains constant, right? So if you're standing, you're not adding force, you're taking gravitational force steadily, right? Nothing's changing in terms of force. So the motor units that are activated to develop the necessary tension in the muscle. So basically, the muscle then changes lengths, and then that's it. Basically, just be able to stay at that stage. Okay. Oh, we're not going to do that. You guys might do that next week. Okay. So I know this one went a little bit long, but I'm glad we got it done. If the last part of that, the tension graphs and the action potentials didn't make a lot of sense to you, I absolutely say do the fills. Do the fills, do the fills, do the fills. I'm probably going to do it this week too, just to remind myself what it's like. Yeah, do the fills. Okay.